215, I think, the schedule says. So how do I need to download this in the laptop, or I just open it there, or?
You put your presentation in the. This is your presentation.
Yeah.
And then you need to
download it first.
I don't understand. Isn't it downloaded? Isn't that how you're seeing it?
This is in the Google Drive.
Oh, yeah. So that's fine. You just need to share it on Blue Jeans. Where's Blue Jeans?
So should we do the share? You guys got that okay? The Jeans session?
Yeah, I'm not sure. Where is the Blue Jeans session?
Oops. Let's it's like you look fancy. Okay, yeah, so the Blue Jeans session was stopped. I don't know why that happened.
You'll need to sign in again. Done.
Oh no. There's too much stuff going on at once.
Kevin and Tomas used some other account. I forget what it was called. It was all caps.
Hey, Kevin? Sorry, ma'am. Where did you get the link for that one? Because I haven't seen that.
Thomas sent an email.
Okay, so I have that.
Yeah, we just got logged out of the Blue Jeans again.
I didn't do it this time. It's not my fault this time. Last time it was.
I'll be sure to close my email this time.
Yeah, thank you.
I was like, oh no.
Well, it was only open because I messed up, so don't.
No, it's okay.
It's really my fault.
I should know better.
It would go through.
There it goes. There we go.
We don't share video. Everything off, audio's not connected.
Correct.
Share.
Yeah, everything's done back there.
Okay.
Okay, so then I have to share or what?
Okay.
So should I download this or share from here, or how does it work?
Oh, yeah, you, oh, it didn't open. Yeah, no, let's.
So this unless I download, right? There's no download.
Wait, you shouldn't have to do that. Hang on. There's a. Did this get rebooted? Hang on.
It's a keynote, yeah.
We use the back arrow on the upper left, right?
Oh, wait, but where's the presentation folder?
Right there, where
This is
your
here.
cursor
Wait.
is.
You can just click anywhere here.
I would go use the back arrow there. Go back to the
Yeah.
folder.
Yeah, but where's the thing that we?
This is the
okay,
presentations
anyway.
folder, so just
Okay.
double click on this.
Okay. Well, that's what you did before, right?
That's all right. Well, go
All right,
ahead
you
and
guys do it.
go ahead and try to
Do
open it.
Yeah.
So then
Wait, it's a key?
it's a keynote.
Yeah.
So go ahead
What
and
happens to
down.
the presentation folder? Because then everything
what
was
is
on the
even
desktop,
the
and you just double click and
Yeah,
it's.
do that. You can download it.
Download.
Not sure why that's happening.
Yeah.
Yeah. Nice. Okay, but then we need to share this.
Yeah.
Right there.
So I have to do play.
Not yet. And now you can play.
Let me see which one is flipping which one. Okay. And then
You need the.
this one is here.
green light, so it's active.
Hello? And there is no, there is no pointer?
The pointer is on that. Well, at home can't. You use that one.
Hello? Hello? Do you hear me now? Good? Good? Okay, good. Yes? Good?
Is the light green?
Yeah.
Yes, yes, yes. The light is...
Now it's
Yes? Yeah?
Very good.
Yep, 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 yep. Yeah.
Hello, hello. Okay, hello everyone. Welcome back from lunch. Today we will be having the second of the star formation and high redshift sessions. So I'll be the chair along with Sinclair Manning, who's online, will be the virtual chair. Sinclair, are you there?
Oh, yep, I'm here.
Okay, perfect. Thanks. Yeah, so we'll be sharing together. Sinclair will be monitoring the chats. And our first speaker in this session is Sultan Hassan, who is a 2022 Hubble Fellow at Princeton.
Okay, so thank you very much. So I apologize to the committee that I had to change my talk to talk about something probably connecting to everyone about a question that might connect to everyone in the auditorium here. It is about how do we really extract information from all the information from surveys, right? So this is the very important thing. And so we know that, right, this is the timeline of all the experiments that we are really excited about, right? And then we know this new generation of the surveys because they have the high sensitivities and they span the large field of views. That requires new generation of models and statistical tools, right? So my talk will mainly be like about probably large scale surveys, but the techniques that I'm going to show should be applicable to all different fields and different things. So if you have a large field survey, right? So Roman or Spherex or Euclid or anything, right? You have these large fields. You want to extract information from there. What do? The easiest thing is to do is to use the power spectrum, but we know exactly the power spectrum. You lose information and you cannot really capture everything. This is just an example for completely two different fields, but if you look at their power spectrum, they're exactly the same, right? So which means that the power spectrum is not really a good summary statistic to these fields, right? So then from the machine learning community side, we know that if you want to extract information from the fields, you need to detect the actual fields and you want to use the fields themselves. And we know the leading technique there is the convolutional neural nets. They achieve really the state-of-the-art performance. Whenever you have fields, if you plug them into CNN, you get everything out. That's known now in the field. And this is just an example. And the convolutional neural nets, basically, it's just like you have a map. This is just an example we did earlier where we wanted to classify between reionization models that either dominated by AGN or galaxies. And basically, the basic idea of training is you will have like many convolutional layers. And the purpose of the training to find the optimal weights and biases that they maximize your prediction. So then if this is the case and we know that CNN works, that we shouldn't really waste our time doing something with CNN, what should we rather do is to try to understand the actual fields. We try to emulate the actual behavior of the simulation in order to do parameter inference and to generate synthetic observations and all that. So then how do we do this? Well, this is normalizing flows. So before I explain what normalizing flows is, I want to just explain what it can do, right? So the nice thing about normalizing flows, it gives you access to two things. So the first thing is that it can generate new examples after it has learned all of your data set. And the data set could be anything. It could be maps, it could be power spectrum, it could be anything that you are interested in. And so what you see here in this example, this is a normalizing flow model that has been trained on Salab A dataset, which is a dataset for high-resolution human faces, and the model is able to generate these fake faces, right? So if I didn't tell you these are fake, you would think that they are really real, right? And then the model is able to recover the small-scale things like the dot in the eye, and also the large-scale picture, right? Not only you are able to generate new examples by normalizing flows, but also you are able to to do parameter inference for free without linking anything to MC, and this is what we call likelihood-free inference. One of the problems with the traditional methods of inference is that you usually, when you have the MC is great, but you need to know what the likelihood is, and most of the time, the easiest thing to assume is a Gaussian field. But they show that in this model that instead of assuming a Gaussian field, you can try to learn the actual likelihood from the data set. And once you do that, you can get really all the posterior distribution. And they show in this paper using this code that has been also developed in the CCA that you are able to recover the same posterior distribution. So this is how once you learn your normalizing flow models in your data set, you are able to do these two things. So I will show you a couple of examples of that. So I wouldn't be able to go into details because of the time, but it's basically the general idea of normalizing flows is that you're trying to learn a mapping between two different distributions. And this is, if you think about it, this is what we do basically in astronomy, right? So most of the simulation we use, we start with a Gaussian field, right? We like a density field or something, and then we try to skew that Gaussian field into the transformation that you like, right? So basically you have a base density you start with, and then you apply this series of neural nets with the specific properties to get your transformed complex density, right? This could be anything. This could be the map you want. This could be your power spectrum, any signal you are interested in. Once this mapping is known, and to satisfy this mapping, so then you can go between right and left, you go forward and backward, all happens just by the change of variable formula. And the basic idea is that the mapping should be differentiable and invertible, and that's it. So then you have to design it in that way. The nice thing is that once this mapping is known, any new example, any random number you draw from this base density, you go through the mapping, you are generating new example of your data set, and any data set you plug into the reverse direction, you are doing inference. And that's the beauty of these models. So because I'm very interested in reionization and on large scale, so I decided to use the H1 maps for this example, but I mean, this example could be one of the things we're doing now. We're doing this for galaxies, like as a forecast to JWST. But let me show you how we do this for H1 maps. So you need data set for that. And I think the camel simulation probably is the best data set we have now. It's just 1,000 of simulations by Simba and TNG, designed for that with varying parameters of astrophysics and cosmology. And this is the kind of different realization you might expect when you use the camels. So I would, and the data is publicly available now in this link, so you can grab and play with any machine learning you want to do. Anyway, so we got that. We got the H1 maps from there. Let's see what we have done. So the first model I developed, I call it H1 flow because it uses normalizing flows, and it's just based on H1 maps. So the basic idea is this is using the first implementation of the normalizing flows that came 2017. And the basic idea is you flatten your maps, you condition them on the cosmological parameters, you pass them up to your base density, and then you learn this distribution with the technique I just talked about now. Then as a follow-up of that, I have been working with Roy. He's a student, was in the machine learning school in the CCA last summer. We were trying to develop, to improve this model. As you will see in a minute, one of the problems with this model is that you flatten the map, so you kind of, the network does not really see the 2D structure of the maps, and that with this you lose information. But in this model, which is called the GLOW model, which is the model that was trained on the human faces, but we use it now for H1 maps, it basically introduces this 1x1 convolution, which captures the details, and in this case you don't need to flatten the images anymore. And this is recently submitted to the NeurOps. We hope that it can be accepted. So let's go. So this is the realization that you can see. So this is here, because of the time, I wouldn't give you a quiz here. So on the right, this is camels, and on the left, this is the realization from the H1 flows. If you look at the images, right, they, on large scale, they look really the same. This is just like training on a 30-minute on a single GPU. which gives you this, which is quite impressive. The only problem with this model now, as you see, if you go to small scale, you can't really capture the filamentary structure that you expect from these models. Then let's go to the H1 below, which is, this is now the real in the top, the generated on the bottom for different cosmological parameters. And you see here the model, the glow model, because of the introduction of these convolutions, you are able to capture the filamentary structures on the small scale much better than the actual camels. Now you can think about it, well, let me try to quantify the difference between these, and now you can look at the power spectrum, right? So what we did here is that you can basically select 1,000 images from camels, take the power spectrum for all these images, and then after you do all 1,000 power spectrum you have, you can calculate what is the mean power spectrum. This is what you see in the top, and you can calculate what is the standard deviation power spectrum, what you see in the bottom, and as a function of the K mode, right? And then what you see here on large scale, the models reproduce the camels quite well. However, the H1 flow does not really capture the small scale because of the reasons that I said, like we flattened the maps and all that. But the H1 below model that we developed recently, it captured this. This is one of the most difficult things, like to capture this high frequency modes in data set. This is one of the most beautiful results I've seen in the field. This is like people struggle a lot to get this small scale power quite right. So we see now we recover that. So this telling, what does this tell us is that we don't need to run the camel simulation. Now we can use the H1 below. You can get examples in a second. You get the same statistics that you expect from the camels, conditioned in the parameters, and then you can do inference. You can do many things much quicker than the camels, because the camels uses Simba and TNG that takes long time to run to get this whole data set. Then we go to the inference part, which is basically the same thing. You can, this is the difference between the inference for different selected observed parameters in the parameter space for H1 below and H1 flow. So the red cross here is basically when you plug into the model the real map with its true parameter. This is what you get here, the red. And then you can generate a grid of random, grid of model parameters from the prior space, and then you plug them with the map to create these posteriors. And as you see here, both models, they are able to recover the true map, except now with the glow model, the contours are much tighter than the H1 flow. This is suggestive that the H1 below is able to exclude larger part of the parameter space, which means that it quantifies things much accurately, and it might be able to break the degeneracies much better than the H1 flow. So this is one example, but this can be applied to anything. This can be applied to, as I said, we are applying this now to JWST images, to many things. So it's a very powerful technique. So in summary, these normalizing flows are very powerful technique. One of the nice thing about them, they give you an access to tractable high likelihood, high dimensional likelihood, which is a very hard thing when we think about the data we're getting from Roman and Spherix and other surveys. Both of them, all the models I showed, they reproduce the camels with the high accuracy. But then if you want to go to smaller scales, you should really maybe do the convolutions and do the H1 below. And these are really fast, like a second you get the maps, which is really impressive. And these, yeah, so these I have showed you, besides generating new maps, you are able also to do inference at the field level, which is something very much needed. And thank you very much for that.
Perfect. Thank you so much. Do you have any questions for me?
Great talk. So you showed that the inference works pretty well, right? When you compare to the true value of these parameters. Are you gonna try to apply to real H1?
Yeah, but I don't think we have them, right? Do we?
Or any other really observable that you can observe in the camel
yeah, we don't have I don't think I have access to any real H1 surveys yet. I don't think there is any real surveys yet. But I agree. I mean, we can, this experiment can be done. I mean, as I said, like in this, from this camel simulations, right, we have access to different fields like dark matter and dark matter fields like emission lines. You can calculate anything to do the same.
And one more question. So obviously the camel simulation makes a lot of assumptions, right? And so would that be important?
Yeah, so that's a problem. That's one of the problems. I mean, there are many collaboration now. They're trying to improve these models, but that's a problem. But this is the best models we have so far, right? So I mean, we can. I mean, the only what we are doing now, we are just preparing for the observations, right? We are trying to develop tools. We show that it works, and the hope that in the future we probably can get better models to apply these to. But training them is not really hard. It's like, I'm very impressed because they take only 30 minutes on a single GPU.
Are questions online, Sinclair, or are we good?
No questions at the moment.
Okay, perfect. Then let's give Sultan another round of applause. And next up, we have Mike Grudich at Carnegie Observatories, who is a 2021 Hubble Fellow.
2 minutes is Oh no, spoilers. Okay. All right. Hey, everyone. So yeah, today I want to talk to you about making stars on computers. So in other words, star formation simulations. This is something I've worked on a fair bit. And I'd essentially like to give you a sort of broad overview of where I'm sort of coming from on this problem, where we're at, and where I think we should be going. And, you know, give a critical assessment of what we're doing well, what we're doing not so well. So star formation is honestly one of the big embarrassments of theoretical astrophysics. All of the things that I know for sure about star formation are on this slide right now. We have some gas, some physics happens, we get some stars. And there are all sorts of really crucial details that are not fully understood. We don't understand why we get a certain IMF and not another, or how that might vary from one place to another, or why stars form at the rate that they do, or how GMCs and star clusters form and disperse, why some stars are in binaries, others not, and how does feedback work? And feedback appears to be at the heart of a lot of these key questions about star formation, actually. So one thing we can do is we can, you know, do some nice simulations, and there's a lot of sort of productive interplays between simulations and observations. You know, we really like it when the observations find interesting discrepancies, new phenomena, and constraints that help us refine our models, maybe consider pieces of physics we had ignored before. And in return, the models can help us predict phenomena and look for observational signatures of things. You know, where should you point your telescope, how long to expose, things like that. And also provide interpretation of ambiguous data, because if you're modeling this observed thing, you have all of the information instead of some, you know, 2D image frozen in time. And another cool thing you can do with simulations is you can disentangle the signatures of different physical processes by just varying the different parameters in the simulation. And this really helps build intuition for the roles of different physical processes in complex systems. Now, these two are my favorite things to do, but I don't do enough of them because they really rely on your simulation having actual predictive power. And it's actually tough to get that, to be getting out things from your simulation that are beyond just what you're putting in and just come from the physics. So why is that tough for star formation? Well, for one thing, everything depends on everything else in star formation. There are so many different pieces of physics that are all talking to each other, and it can just be a very challenging calculation to do. And you inevitably have to invoke all sorts of approximations to have any hope of treating any of these. And that's quite often where things get a little tricky. Now, that in itself wouldn't be such a big deal, except the dynamic range of star formation is also massive, like a factor of 10 to the 14 between the size of galaxy clusters and large-scale structure down to the size of individual stars. So in practice, you have this sort of finite dynamic range. State of the art is around 10 to the 6 in length scale right now. And that's where you're actually solving physics equations self-consistently. Above that, you're reliant on your assumptions about your initial conditions and boundary conditions. Below that, you're reliant on your subgrid assumptions about what's going on scales that you can't resolve. And worse, stellar feedback, all the different ways that stars can push around and heat up the gas around them, means that getting it wrong on small scales can propagate back up to larger scales. So that makes it really, really tricky. So when I came into the field, we had this new generation of more physically predictive galaxy simulations, and what they were able to pull off was treat all the different kinds of stellar feedback, well, almost all, and have unprecedented resolution. And they were able to do things like get the Kennicut-Schmidt relation, thin disks, satellite populations, all sorts of different phenomenology, essentially for free out of the simulations just by doing the physics right. So this was great. That was some serious predictive power. And it was around this time that I started using similar techniques to the fire simulation shown here at much higher resolution to do these sorts of GMC scale simulations to work out how feedback works on these scales. So this is what I was really interested in, and indeed, this sort of generation of galaxy simulations, resolving the multi-phase ISM, sort of proliferated, and people ended up using it to do all sorts of studies on the properties of star clusters and giant molecular clouds, and, you know, really try and get at a lot of these questions about star formation. And, you know, I'm actually on a couple of these papers, but something always bothered me when we were doing this, which was that none of these simulations are actually making any stars, right? They're not getting to that level of self-consistency. They have some sort of bogus rule for why a blob of gas should one day turn into a blob of stars without really working out the details of the individual stars. So does this matter? Well, essentially, anytime anybody has actually investigated the impact of these sorts of subgrid choices for star formation, the answer is yes. It impacts how much dense gas you have, what masses of GMCs you have, your star formation histories in your GMCs, and your star cluster mass functions. So the key uncertainties on these sort of GMC and cluster scales in galaxy simulations are the details of massive star formation, so when, where, and how they form, and the star formation prescription. How should we convert an unresolved blob of gas to a blob of stars? So I decided to just try and brute force this problem and simulate star formation directly with all the physics I thought might be important. And this was the idea of the StarForge project. So the idea of the StarForge project is we are doing these GMC scale simulations following individual star formation at high enough resolution to resolve the entire stellar mass range of the IMF and predict it self-consistently, while treating all the different kinds of physics we might think are important, including all four kinds of major feedback relevant on GMC scales: protostellar jets, stellar winds, supernovae, and radiation. And this was the first time this had been done. So just to show you the kinds of processes we're able to study in these simulations, this is a movie of the first calculation we did with the full physics package. So we have a 10 parsec cloud with 20,000 solar masses in it. We let it go with some initial turbulence, and it sort of undergoes this kind of turbulent filamentary collapse where you get these overdense regions that are starting to form individual stars where these cores go on to collapse. And as these individual stars form, they accrete more and more. And as they accrete, they're also throwing off all of this feedback material, mainly in the form of jets for low-mass stars. But everybody has to grow up, and a lot of these low-mass stars just accrete and accrete and accrete and become lucky and get to become high-mass stars. And when they do this, they have all these ionizing photons and winds, and they drive these expanding Stromgren spheres and essentially turn the cloud into a Swiss cheese of feedback-driven bubbles. And at this point, we've sort of assembled a lot of the stellar mass into a central cluster, but while this is all going on, feedback is also really powerful, so we're just blowing the whole cloud apart and opening up a big cavity, and that's when star formation starts winding down, and you reach the sort of endpoint of star formation. So the winds and the radiation have disrupted the cloud, and then the first supernova to go off just puts the nail in the coffin. So we're left with an actual outcome of star formation run all the way to the end, And this is the first time this has been done with all of the relevant feedback mechanisms. So we've been using this for all sorts of cool stuff. You should check out David's talk coming up next, where he'll talk about the IMS. But one other thing we've done is work backwards. So we took that simulation and ones like it, and we downgraded its resolution down to something that would be feasible to run in a galaxy simulation, and ran it with the FIRE model. And we're comparing the star formation history, so the star formation efficiency of these different cloud models at these different resolution levels. So the blue ones are StarForge, and the other ones are various resolution levels for the FIRE-like setup. And interestingly, we find that the FIRE-like one actually forms stars much too rapidly initially. It kind of converges away a little, but not any realistic resolution. So that sort of tells us that the subgrid star formation prescription is probably a little bit too aggressive, too fast. So the first order correction might just be to slow things down. So we're going to be working to sort of refine this and figure out what are the sort of leading order corrections to these existing prescriptions based on what we find in StarForge. But StarForge still suffers from a fundamental issue, which is that we do start from this sort of silly-looking uniform density spherical cloud. And while it does form these sort of somewhat realistic-looking structures as it evolves, we would really like to do something better because, as Catherine will be happy to tell you, real GMCs are not uniform spheres. So in this paper with my former student Henry Lane, what we did was try to do something a little bit better. So we came up with a new simulation setup where we just put the gas sphere in a confining potential and applied a stirring force to just try and stir it up into this, highly substructured, nominally more realistic-looking state before we switch on gravity and form some stars. So this is a little bit better, but one sort of startling thing that came out of this, we actually performed a controlled comparison between what we get in simulations that are identical except for their boundary conditions. And we found that the simulation with vacuum boundary conditions, in other words, the cloud is isolated, behaved very differently from the one with periodic boundary conditions, despite the local conditions being statistically identical. So that tells us that boundary conditions are a huge deal as well for the results of these star formation simulations. So we really need that larger scale galactic context to get the right answer. So why is this? Well, another startling thing that came out of these simulations is that, well, here we're looking at the size of the gas reservoir that contributed 95% of a star's mass as a function of the final mass of that star. And what we see is that the most massive stars actually form out of gas flows that are comparable in scale to the parent cloud itself, which is 10 parsecs. So massive star formation is not microphysics in this sense. It's coupled to the cloud scale. So scales that are resolved right now in galaxy simulations directly coupled to the way massive stars form and accrete. So, okay, what do we do with this? So we know star formation is kind of hard to do due to all of the multi-physics and the large dynamic range and the fact that feedback sort of couples all the scales together. The galaxy and GMC scale models both have their issues, right? And these issues always appear at the edge of the dynamic range that they're able to handle. For the GMC scale simulations, they can resolve all these small scale dynamics of feedback and star formation, but they don't know anything about the galactic context and the boundary conditions. Whereas the galaxy simulations can provide those initial and boundary conditions for star formation, but they can't handle the small scale physics. So where do we go with this? Well, we need to bridge the gaps in scales. We need to account for all the key physical processes while essentially trying to bring the predictive scale of galaxy simulations to smaller scales while also increasing the predictive scale of the high resolution StarForge simulations. So in the short term, what we can do, as I was hinting at, we can just come up with some new subgrid recipes calibrated to the StarForge simulations that anybody can just put in their galaxy simulation. In the medium term, what we'd like to do is some galactic zoom-in simulations where you choose just a GMC of interest that forms in a simulated galaxy, and you re-simulate that at very high resolution. And that way you capture the galactic environment. In the long term, what would be really cool is some sort of crazy exascale code that can just take these StarForge simulations and scale them up to, a KPC patch or even a whole galaxy. So that's where this might be going. Definitely we'll do these first two. This third one we'll see. And I'll just end on a promising note that I think there's actually a lot of agreement on what these key issues are with the star formation simulations, and in fact, 3 of us are actively collaborating on doing these different things. So there's a lot of Hubble brain power being devoted to this right now, and others are, of course, welcome to join. All right, thank you.
Okay, perfect. We have time for one quick question.
Yeah, thanks for the great talk. In your Starforge video, the protostellar jets seem to show up very brightly. I was kind of wondering if you could speak to the relative importance of that early feedback versus the winds and photonization, and sort of doing that initial evacuation around the star cluster. What's the relative importance of the different early feedback that you have?
Yeah, so actually, we've been finding that protostellar jets actually transport a comparable amount of feedback momentum to the other feedback channels like radiation and winds. And in particular, before you have your very massive stars, they're all you've got. So actually, they are the key feedback mechanism for determining the early star formation history of the cluster before those really massive stars get going.
What's the physical, gas resolution?
Nominally, in this one, 10 to the minus 3 solar masses.
And what's your star formation?
It's complicated. We can maybe chat about it offline. It's a bunch of different checks for boundedness and converging flows and all that sort of usual stuff. But yeah, it's sort of inspired by the Bate sync particle algorithm, but it's a little bit more developed and sophisticated.
But in the end, there's still a subgrid level of it.
Oh yeah.
You're still not actually forming stars.
Yeah, that's a fantastic point. Yeah. Basically our dynamic range.
Down, but
yeah.
It's still a subgrid.
Yeah, so these are sync particles with a radius of nominally 30 AU. So, that's where our self-consistent dynamic range starts. So, we can do a lot of things with that. But yeah, there's all sorts of interesting stuff going on smaller scales that we are definitely not capturing.
Okay, perfect. So I think we're out of time. So let's thank Mike again.
Thank you.
Okay, so next up we have David Guzhinov. To probably pronounce your last name wrong, I apologize in advance. But I'm going to give you a 2-minute warning if that's okay, David.
Sure. Can I share my screen?
Yeah, share your Zoom. We can, let me see. Wait for a second until we can see it, and then you can start.
Is it visible?
It is, but it's not full screen.
Okay, let's start again. Sorry about that.
Okay, you're good to go.
Okay, so hi, I'm David Guzhinov. I'm also a Hubble Fellow at Harvard, and I'm really sorry that I cannot be there to give this presentation, so I hope this virtual version will suffice for now. So I'm also working in the Starforge collaboration like Mike, and I'm very interested in star formation. And specifically today, I want to talk about feedback and the role of different feedback in particular regarding the initial mass function of stars. So just to make it clear about what I'm talking about, so what I'm talking about is the part of star formation where newly formed stars influence their surroundings, so that they influence their own accretion flows, but they also influence the environment in which future stars can form. So this is what we refer to as feedback. And the main processes that we'll be investigating are protostellar outflows, radiation, winds, and supernovae. So similar to Mike, as I'm also in the Starforge collaboration, and I think he gave a very good intro to it. So I would just quickly summarize that these are GMC scale simulations that are able to resolve down to stellar scales. So your sync particles, you know that they represent more or less just one star. So we could say that it has individual star formation. And also it includes essentially most of the relevant physics of star formation. So what we were curious about is what does each piece of physics contribute to setting the IMF? And what we came up with is a suite of simulation, which we call the physics ladder, which is just a set of simulations with identical initial conditions, but with progressively more and more complex physics involved. And you can see that these latest rungs of this physics ladder are the ones which have feedback. We also have another suite which concentrates on the latest rung, where you have all the physics included. If you recall, I said that this physics ladder was run with identical initial conditions, so it makes sense to actually check how sensitive your final result is to initial conditions, which we did with the all physics version. So these are the two suites I will be talking about today. Okay, so first, let's talk about what the physics ladder suite. So we have been working on it for some years. So I'm just going to quickly run over the first few results. So first simulations were just gravity and turbulence. And if you do that, what you find is that your stars or sync particles are just basically numerical. Your gas fragments down to your numerical resolution. If you add magnetic fields, however, then you do get an IMF out of it. You do have a physical mass scale for your stars. The problem is it's just way too high. It's not what you observe. It's like a factor of 20 or 30 higher, and it's also very sensitive to initial conditions. So naturally, the answer is to add even more physics, for example, including non-isothermal thermodynamics or protostellar jets. So if you look at this plot, this is showing the sync particle mass spectrum, which is basically a proxy for the IMF. Then you can see that here with the magnetic field version, you get something, but it has basically no resemblance to the canonical IMF. If you add non-isothermal thermodynamics, you get the blue line, which, you know, is better, but still kind of awful. But if you add feedback, and in this case just protostellar jets, suddenly you get something which is much more like the observed IMF. Actually, it is more or less within observational uncertainties of the observed IMF, and we didn't even add any of the other physics. So that sounds very nice. That sounds very good. So we actually only need jets for the IMF. Is that the most important feedback process? Not quite. So the problem with jets is that they can't quench star formation. So your star formation just continues essentially to very high star formation efficiencies, unphysically high ones. Also, your massive stars, so the star formation is not equal among stars, this runaway star formation, only your massive stars will accrete more and more. So the more you wait, the more you run your simulation, the more of your gas will end up in the most massive stars. So let's add more physics and see if that changes things. And if we just look at the IMF at this fixed 7% star formation efficiency, then adding radiation and winds, if you look at the plot, it doesn't, I mean, there's a slight shift relative to the protostellar, relative to the one that only had jets, but it's essentially the same. So does radiation and wind do nothing? Is it not important? Well, if we look at these two videos, so two rounds, one with jets only, no radiation, and one which has radiation, we quickly realized that radiation plays a very, very important role, which is to provide a natural endpoint to the simulation. Because in this case, star formation ends, and in the case where we only have jets, it just does not. Okay, let's move on to parameter variations. So what if we add all the physics and just vary our initial conditions? What's going to happen? So as you can see, we varied a large number of initial conditions. What was very interesting is that we found that even though the star formation histories, so how stars form over time, differed greatly relative to initial conditions, we found that the IMF didn't really change. For example, if you varied your surface density or virial parameter, the IMF didn't really change if you did that, which is actually great because that's something you would need to explain the near universality of the IMF. So what's happening here? How can we explain this? Because one issue with this conclusion is that many previous works have actually come to an opposite conclusion, that the IMF should vary with these, and it was a perplexing thing. How can it be ubiquitous then? And the solution seems to be a fairly simple one, actually. So most simulations, previous work, including my own, what we did is we made plots like this, where you look at the IMF at a fixed star formation efficiency. But the thing is that the final star formation efficiency varies with initial condition as well. Also, if you look at as a function of current level of star formation, what, for example, the IMF peak is, that's basically the median mass of stars, it changes. So if you stop at a fixed point in SFE, you might get big differences, but if your final SFE is different, it might be reduced. And that's actually happening. So at fixed SFE, this is the low surface density one, this is the high surface density one. We have basically half a dex difference here, but the final star formation efficiency is 1% here and something like 15 here, and that basically allows the high surface density run to catch up, and you end up with a final variance which is much, much smaller. However, it's not true to say that we found that the IMF does not vary at all. We have this nice compensation effect between final SFE and, for example, surface density that negates the variation to the surface density and real parameter. But when you vary something like metallicity or magnetic fields, you do get some more substantial variations. So specifically, if you vary metallicity, you shift your peak to the right a bit, but not much. And if you vary your magnetic fields, you can make the IMF a bit steeper. So these are significant variations, but actually more or less within observational uncertainties. So we haven't done an in-detail study yet, but there are indications that we might be able to explain IMF universality here. All right, then I will just move on to summarize what I wanted to say today. So the Starforge collaboration investigated two aspects of star formation here. One, what does each piece of physics contribute to the IMF? And what we found is that you need feedback. That's basically the most important part. You need jets to essentially set the peak of the IMF, and you need radiation and winds to more or less disrupt the cloud to end the process. And it's actually an important thing of where that process ends, because if it ends later, then you have a higher star formation efficiency, so you end up with, you allow your star formation masses to rise higher, so that basically negates some of the variations that you would find at a fixed star formation efficiency. I didn't really talk about supernovae, but basically the reason for that is that in these simulations, they come a bit too late. We are in the progress of looking at larger GMCs, so like 200,000 solar mass clouds, and see if maybe in them they occur early enough, but so far it doesn't seem to be happening. It doesn't seem to be so. All right, I'm not sure how I'm with time, but let me know if you have any questions.
So you were perfect on time, and so we have time for lots of questions. Any in the audience? If not, I have a question, actually. Can I start? Okay, so I have a question about, so you place a lot of constraints on the IMF, and I'm wondering whether you place any similar constraints on the core mass function and the relationship between the core mass function and the initial mass function. Can your simulations tell us anything about that?
So that's actually that the previous speaker, Mike, has investigated a bit. The main issue with this, with looking at the core mass function is what is a core? What's the definition of a core? And there are two ways to go about this. One is to come up with a theoretical definition. That's what I think Mike did. And in that case, which is basically saying it's a isodensity contour with some defined virial parameter. But in that case, we didn't really find a correlation between final stellar masses and core masses. A better comparison would be to do a synthetic observation and do exactly what observers do, go through the same analysis. This is something we are planning to do in the future, but we haven't had time yet.
Okay, perfect, thanks. Are there any questions? So I'll take one from the audience, but are there any questions online by any chance?
Nope, not right now.
Okay, thanks.
Great talk. This is Jake. I'm an exoplanet person, so this is going to be a very simple question. You were talking about the universality of the IMF. Does this also hold for other galaxies besides the Milky Way?
Yes, so that's actually one of the interesting questions that we are following up on. So the variations we have tested were, in the Milky Way context, they were fine, but, in more extreme galaxies, there are a lot more extreme variations. So yes, we do have simulations in progress. They haven't run yet, where we try to mimic some of the initial conditions that you would find in like a Euler and other more extreme galaxies, to see if we can really make the IMF different and maybe reproduce some of the inferred results that they did with like early ellipticals, where they have a very bottom-heavy IMF was inferred from observation. So yeah, we are looking into that, but those simulations just haven't run yet.
Hey, David. Great talk. This is Ryan. So on the high mass end of the IMF, it looks like you basically get that right only with the addition of thermodynamics, and the other feedback you added in didn't really change the high mass part of the IMF. I was just wondering if you could maybe speak to why that is. I mean, do the earlier forming high mass stars, they're not really regulating the later forming high mass stars or something like that?
Okay, so it's actually something we struggled with a while. If I understand the question correctly, you are asking about this high mass end, and maybe it looks better here. And the thing is that if you look at this red one, then it looks like, oh, you don't recover the saltpeter. So there's no -2 slope there. That's what it looks like. But actually, that's not the case. It's just that our cloud is, so what happens is that magnetic fields would imprint a mass scale where the -2 high mass slope would turn over, and it's just for Milky Way average quantities, it would be a very high mass. And just because our cloud was, 20,000 solar mass, that's why we don't really see the high IMF continuing down here. But if you had, ideal MHD, gravity, and turbulence, and just these, and just put an enormous cloud into it, you would actually see it extend more. So that -2 slope, it's a product of a depth similar process, essentially, as far as I understand. Or if the question was about the cutoff of the high end, that's something that we are looking at, and that's something definitely related to feedback. but we right now don't have enough runs to, well, to really statistically talk about it with any certainty.
Okay. I'm going to have to cut us off. Thank you so much. We're out of time for questions, but let's thank David again. And so next up we have Viraj Pandya, who is I believe, a 2021 Hubble Fellow at Columbia University.
Yep.
All right, take it away. Thanks.
So I have to share my screen, right? I think. Where's the thing for that?
You think you have to go to Blue Jeans?
Where is that?
It's this thing right here.
Oh, okay.
And then desktop.
Okay, cool.
And then there you go.
Sweet. Okay, thank you. All right. Hi, everyone. My name is Viraj Pandya. I am a first-year, soon-to-be second-year Hubble Fellow at Columbia, and I want to take a second to thank the leads and the SOC for organizing this amazing symposium. It's been great to be able to be here in person and meet many of the fellows and see all the amazing things that you're all working on. So I'm excited to tell you about some work that I've been doing over the past few months on the connection between galaxies and their circumgalactic medium. This is work done in collaboration with Drummond Fielding, Greg Bryan, Chris Carr, Rachel Somerville, and the FIRE team. So we've heard throughout this week, and even just in this session, that galaxy formation is a result of numerous physical processes like gas accretion and star formation and feedback in the form of, for example, galactic winds and so on and so forth. And all these physical processes leave an imprint on the circumgalactic medium, the diffuse halo gas around galaxies. And so something that we would love to have in the field is self-consistent, time-dependent models for the connection between galaxies and their CGM and how they co-evolve. And so, of course, we have a number of amazing, beautiful hydrodynamical simulations that we've seen just in this session and throughout this week. And these are great because they can make detailed predictions for the properties of galaxies as well as gas flows in and around the CGM. But we would still like a simpler model to interpret the predictions and inner workings of these kinds of numerical experiments. And so along those lines, there are many compelling 1D CGM models, such as steady-state cooling flow solutions on the top right, and hydrostatic equilibrium models on the bottom. And these are compelling because they're able to describe the structure of the CGM, both in simulations as well as in observations around real galaxies. For example, in terms of the temperature and density profiles of the diffuse gas and the abundances of different ions and so on. However, these 1D CGM models are generally static in time, by which I mean that they describe the properties of the CGM at a single instant, and they don't try to simultaneously model the galaxy formation process. And so I want to introduce an alternative complementary approach where you take everything that you think you know about galaxy formation and you package it up into a system of coupled ordinary differential equations. And these ODEs will tell you the time evolution of various state variables that you will define to describe your system. So, for example, some basic things that we might want to know about our system is what is the total mass in the CGM, what is the total mass in the interstellar medium, the total mass in the long-lived stellar population, the metal masses of the three different components. And this idea of writing down the m dot mass flow ODEs and the m dot z metal flow ODEs traces back decades to the 70s. This is the underpinnings of a classical technique known as semi-analytic modeling. And so the thing that I've been asking is, how do we build on this promising framework and improve its realism? And in particular, how do we use it to make predictions for the thermodynamic state of the CGM as a function of time, at least in a global sense. And so the way that I've been pursuing that is to write down two new ODEs that will tell you the time evolution of the total thermal energy in the CGM and the total turbulent kinetic energy in the CGM. And each of these individual terms on the right-hand side has a functional form that's associated with it. I can't get into that in the interest of time in this talk. But each of these individual terms describes an individual physical process that is part of this global gas flow cycle, also known as the baryon cycle. And so I want to just describe a few of these terms. So let's take this first ODE for the evolution of the thermal energy of the CGM as an example. So this is going to be given by a combination of different terms. So for example, the rate at which thermal energy is brought into the CGM from cosmic accretion minus the rate at which thermal energy is lost via radiative cooling plus the rate at which thermal energy is generated inside the CGM as turbulent eddies dissipate. Plus the rate at which thermal energy is pumped into the CGM from supernova-driven winds coming out of the galaxy, and then minus the rate at which thermal energy is lost to the intergalactic medium as the CGM eventually gets overpressurized and has to vent its excess energy. So we could keep doing this all day with all the other terms, but I want to move on in the interest of time and tell you what we envision for the structure of the CGM in this model. So let's say we're at some time along the evolution of any individual halo. At this time, we know the values of our state variables from our ODEs. And so, for example, we know the total CGM mass, so we assume in this model that CGM mass is distributed with a density profile that goes as a power law. The slope of this power law is a free parameter in our model. We typically take a value that's consistent with a cooling flow solution, but you can play around with that parameter if you wanted to. And then the normalization is just set by requiring the integral of the density profile in the spherically symmetric model to add up to your known CGM mass. Similarly, we have a temperature profile in this model that we also assume to be a power law. And we typically take the slope of this power law to be 0, to be a flat profile consistent with a cooling flow solution. And then this is where we diverge from previous approaches. So whereas previous approaches coupled the thermodynamics of the CGM to that of the underlying dark matter halo, in the sense that it was assumed that the CGM temperature everywhere is going to be the virial temperature of the dark matter halo, we can actually solve for the normalization, this T0 parameter out front, by requiring the integral of the thermal energy in these radial shells to add up to the known value of your of the thermal energy, which is the state variable. So that's the second thing. And then the third thing is that we imagine that there are large-scale turbulent eddies distributed throughout the CGM with a variety of sizes. And these turbulent eddies are driven by both cosmic accretion as well as by supernova-driven winds. And this turbulence provides two things. It provides a large-scale pressure support so that even if you had maximally cold and dense gas, it can't just free fall into the ISM and, for example, form too many stars. And this turbulence also provides a heating term to the CGM because as it dissipates, it'll get converted into thermal energy. So we have to specify two things about the turbulence in our model. The first is what is the characteristic turbulent velocity of these large-scale eddies, and so that's just going to be given by the square root of 2 times the kinetic energy over the CGM mass that we know in the model at this time. And the second thing we have to specify is the time scale on which the largest eddies in the CGM will cascade down to ever smaller scales and eventually dissipate as heat. And so that is given just by the ratio of the largest turbulent eddy size divided by this characteristic turbulent velocity. Now, we don't know how this turbulent this R-turb parameter should scale with halo mass and redshift and different CGM and galaxy conditions. So we make a simplifying assumption to start that this R-turb parameter is proportional to the halo virial radius as a function of time. So that's the gist of the model, and we're now working on various initial applications of this model. And so the first thing I want to do is highlight some work that's being done by Chris Carr, who's an excellent grad student at Columbia. Chris has been taking this model and forward modeling the observed stellar to halo mass relation. And specifically, he's exploring the parameter space of 2 parameters in our model related to galactic winds. So one is the mass loading factor, which is the ratio of the mass carried by galactic winds out of the galaxy divided by the star formation rate. And the other parameter is the energy loading factor, which is the ratio of the energy carried by the galactic winds divided by the energy originally produced by the Type II supernovae in the ISM. And so what we're finding is that when you vary the mass loading factor in our model, the stellar to halo mass relation is not very sensitive to variations in the mass loading factor. Instead, it's really variations in the energy loading factor, or equivalently the specific energy of the winds, as shown on the right, that lets you reproduce the range of observed stellar to halo mass ratios observed or empirically determined for a wide range of halo masses. And the reason for this is that in our model, the CGM is in some sense self-regulated. So if you keep dumping a bunch of mass into the CGM, you're going to increase the density. you're going to decrease the cooling time, and then you're going to have all that stuff kind of rain back down in the galaxy and form stars again. However, if you preferentially launch high specific energy winds, that can raise the specific energy of the CGM, prevent further cooling and accretion into the ISM, and you can still reproduce the observed stellar to halo mass ratios, as well as ISM gas fractions and so on. So that's one application that we're pursuing on the observational side. Another thing that we're working on is to ask, well, can we use this kind of framework to understand the evolution of individual galaxies and hydro simulations, both for a single suite of simulations as well as eventually between different groups of simulations. And so to start as an initial test bed, we're using the FIRE 2 cosmological zoom-in simulations that you heard about from David and Mike just in this session. And so whereas Chris before was kind of blindly exploring the parameter space of only 2 of our model parameters, with these simulations, we can just go into the particle data and measure the values of multiple parameters of our model. For example, the ISM depletion time and its dependence on redshift and halo mass in the top left. You got the mass loading factor and the energy loading factor of the winds. You have the metallicity of the winds on the bottom left, or equivalently the metal loading factor, and then you have the metallicity of the inflows at the halo radius. So once we have this part of a parameter space pinned down by the simulations, we can run this model on merger trees of individual dark matter halos extracted from these simulations and see how well we compare in terms of various properties. So the first thing we might want to know is the mass assembly histories of the different components, the CGM mass, the ISM mass, the stellar mass, as a function of time. And so I'm showing you there's 12 panels here for each of the individual core FIRE 2 halos. The solid lines are the measurements of these properties from the particle data, and the dashed lines are the predictions of our model. And you can see that we're getting pretty close to these sophisticated simulation predictions over a huge range in halo mass scales, from ultra faints in the top left to Milky Way mass halos in the bottom right. We can also talk about the baryon fractions of the halos, and so we also reproduce the result in the simulations that dwarfs have preferentially lower baryon fractions, and our model can tell you why this might be happening. So it happens for 2 reasons in our model and in FIRE. One is that the dwarfs preferentially do not accrete their full complement of the cosmic baryon fraction because there's large-scale heating from supernova-driven wind shocks and photoionization from the UV background. And 2, these dwarfs also have a significantly overpressurized CGM, and so they're driving large-scale outflows of previously accreted baryons, leading to these preferentially low baryon fractions. So that was mass assembly histories. We can also look at the baryon cycle, by which I mean the gas inflow and outflow rates. So I'm showing from left to right here the gas accretion rates at the halo radius, then the CGM cooling rates, then the galactic wind mass outflow rates, and then finally the outflow rates of mass out of the halo. And you can see again across this huge range in halo masses, we're reproducing as a function of time and halo mass very closely what we measure in the simulations. And for completeness, we also reproduce the metal flow cycle as well. So one last thing I want to leave you with is that our model also predicts something new, which is that the CGM should undergo a phase transition, in the sense that at early times the CGM is in a relatively cool but turbulent phase, and at some point it transitions to a warm, hot, thermally supported phase. And so here's an example evolution of a Milky Way mass halo. In black, I'm showing the time evolution of the halo virial velocity. In cyan is the turbulent velocity, or equivalent the specific kinetic energy. And then in red is the sound speed, or equivalent the temperature on the y-axis of the CGM. And you can see at early times, the CGM is relatively cool. The temperatures are 10 to the 4, 10 to the 5 Kelvin at early times, but it's also very turbulent, with the V-turb being comparable to or exceeding the halo virial velocity. But at some point, there's a transition, the turbulence decays, and the CGM temperature shoots up to roughly 1,000,000 degrees Kelvin, like we observe around our own galaxy today. And this just comes out naturally from the model because we're keeping track of the energy flow cycle in the CGM with those 2 E.ODEs that I introduced earlier. So I can say a lot more about why this phase transition might happen and the results for other mass scales or halo mass scales, but I'm going to stop here. And I'm going to leave my summary slide up and say that this is just a start, right? There's much more physics that we need to account for in these kinds of models. And so we're thinking about extensions to this model in terms of black hole physics and satellite physics, and possibly making a multi-phase CGM model. And later in my fellowship, I'm very excited to take this model and make predictions for observables for not just the galaxy population, but also the CGM, because we think that CGM observations can break many degeneracies in the hugely multidimensional parameters based on these kinds of galaxy formation models. So I'll stop there and take any questions. I think we have a bit of time. So, thank you.
Do we have time for one question? Questions? Sorry, Lee.
Yeah, very nice talk. Thank you. So I have a question about your last point about the phase transition. So what determines this epoch of this phase transition? Also, are they coincident with the time when the disk start to settle? So anything related to that?
Yeah, that's a great question. Thank you for that. So basically, it comes down to a balance between your radiative cooling and whether it can keep up with your different heating terms. So the way that the best way we thought actually understanding this is that we have a system of ODEs, and we can look at the time evolution of the equilibria of these ODEs. And so what I'm showing here is that same Milky Way halo. The top panel is the same panel you saw before, but these bottom two panels show E dot thermal as a function of the CGM temperature, and then the E dot kinetic versus the V turbine parameter. And where these black lines go to zero, that's an equilibrium for the model. And I want you to focus on the cyan line here, which is the cooling curve. And so as time marches on in this movie, you see the cyan line, the cooling curve, go down. And this is primarily driven by the fact that the mean density of the universe is going down. So since cooling goes as n squared lambda, eventually cooling cannot keep up with heating, and you have this huge, you just have this sudden jump in the temperature. So it's actually it's surprisingly simple, but then there's the details of what you assume for the rate at which the eddies will decay and so on and so forth. So we can talk more after also.
Okay, perfect. So I think we're out of time, so let's thank Viraj again.
Thank you.
And our last talk of this session and of the day will be by Ariana Long, who is a 2022 Hubble Fellow at UT Austin.
Maybe. Thank you. Yeah, it disappeared. Oh, you did?
And then there's presentations.
There we go. Thank you. But the real question is oh, it did do it. Great. Wonderful. All right, let's do these. What's wrong?
Oh, you didn't share. Okay.
Okay. So
blue jeans right here. Oh, you didn't share your whole desktop? It is shared? Okay. No,
is it working? Can folks online see this? Okay, great. Oh, someone must have disabled closed captions. Okay. All right, can y'all hear me? Everybody can hear me? Okay, great. Do a little testing. Just going to turn it off. No, it's a laser. Okay. Hi, everybody. My name's Ariana Long. So nice to meet y'all. I am an incoming Hubble Fellow. So today I'm just going to talk to you a little bit about the finale of my dissertation. And then at the end, during the future work, I'll talk a little bit about some of the stuff I hope to do during this fellowship. This is not going to be about any simulation or subgrid physics with star formation. This is actually a numerical model that I made out of frustration about galaxy evolution. So I'm sorry to disappoint you. There's no stellar physics in here. My thesis was primarily about massive dust-obscured star-forming galaxies in the intermediate and early universe. And so I want to emphasize here, as Sinclair kind of mentioned earlier, dusty star-forming galaxies originally were discovered because of their extreme dust emission. After about a decade of studies, we've learned a lot more about them. They're not a homogeneous population. And so while I will use DSFGs or dust-obscured galaxies throughout this presentation. I will also continually emphasize how different they can be and how really they are an important population to study as a phase transition for massive galaxy evolution, not exactly as their own population in and of themselves. So some of the interesting things about these galaxies is their excess star formation rates. So such prodigious star formation, lots of O and B type stars being formed really quickly and early on, creates an abundance of dust. And this dust creates kind of the shield. That dust absorbs the UV and optical emission and re-emits in the infrared. And so when you actually kind of go into the cosmic volume, you have a light cone, you slice it up during different epochs, and you sum up all of the star formation that is obscured by dust versus unobscured, so UV bright star formation. You get this cosmic star formation rate density plot over here. And the orange curve traces that obscured part, and that blue curve traces the UV bright part. And what you can kind of take away almost immediately is that obscured star formation dominates in the intermediate universe, potentially playing an important role out in the first 1 to 2 billion years. That is still highly up for debate. Ask me about that later. All this prodigious star formation creates really massive galaxies really early on. This is why I care about them in particular. Over here you can see this is a star-forming main sequence, so stellar mass of the galaxies on the abscissa, the x-axis, star formation on the y-axis. And while they are fairly diverse across epochs, in general they are on the more massive end. They tend to be about 10 times more massive, an order of magnitude more massive than a normal Milky Way type galaxy. And finally, because of all that prodigious star formation rate, if you do really, really simple calculations, a closed box scenario on each of these galaxies, you have a measurement of how much gas they have, and you know how quickly they're forming stars. You can back out a gas depletion timescale. It's pretty naive, but it is an interesting indicator to us that these galaxies have depletion timescales on the order of millions of years, so tens to hundreds. Whereas more normal steady state galaxies, again, like Milky Way types, are on the order of 1 billion years for their gas depletion timescales. And so the picture I want to paint here is that these dust-obscured galaxies are kind of the live fast, die young type of galaxy. They grow really, really fast, really early on, and they also tend to die earlier in the universe. But they are very rare, and I would say about 1 in 1,000 during their peak in population, which is again around redshift 1, 2, or 3. And so some folks say, oh, that's a rare galaxy population. Why do we care about them? These galaxies actually have a lot of interdisciplinary implications. So on the kiloparsec, parsec level scales, we're talking about the most efficient forms of star formation within their GMCs. And so these are great places to study extreme stellar feedback and hard ionization fields and how galaxies are able to sort of survive, or stellar clouds are able to survive that. This also includes interstellar medium ISM enrichment, so some of the first elements, the heaviest elements being formed really quickly over short periods of time. All that dust creates a nice cooling environment for these birth clouds and things like that. On more megaparsec scales, other than just general galaxy evolution, this is really particular to also the most massive galaxies, and therefore things like overdensities, galaxy clusters, massive halos, large-scale structure even. And there is actually a body of work in the last few years that is suggesting that dusty galaxies are kind of a signpost potentially for protocluster environments, maybe even making up those brightest cluster galaxies in the center of galaxy clusters that we see locally today. There's really massive behemoth spheroidals. And then finally, on the more cosmological scales, we're talking about major contributors to the cosmic infrared background. And I already mentioned a little bit about large-scale structure, and I also showed you that plot earlier about just cosmic star formation history in general. So again, these galaxies, while rare, are very, very important to lots of areas of astrophysics, including in our simulations. But yet, we don't really know everything about them. From an observer standpoint, there's a lot to learn still. Part of that has to do with their rarity. So due to a lot of instrumental limitations, things like field of view, or even really large PSF, so point spread functions, where these sources are blended together even when they're not at the same epochs, they're just projected together. Things like that really, really mess up our understanding and kind of keep us from really fully quantifying this population. Other issues such as lack of population homogeneity, so As Sinclair kind of mentioned, some of the OIR dark, the near IR dark ones that don't show up at all. Sometimes we do get UV emissions, sometimes we don't. Things like bias selection techniques, so depending on where they're selected in the electromagnetic spectrum, you can get totally different population properties. But my main focus for today and for this work is on the discrepant number density estimate. So really, literally just how many of these galaxies exist during different periods of time in the universe. To me, that is a first order issue that needs to be solved before we can even understand how they get to be the way that they are or model them. We need to know how many there are so our models can even start producing them. And just to kind of drive home that point, a lot of our best models, hydrodynamical, semi-analytical, all those best cosmological models really struggle to produce these galaxies. Some of them that do actually produce them, so like the original Illustris did pretty good in a 2D projection kind of image on sub-millimeter bright galaxies, so these dusty galaxies. Even though it did pretty well there, it couldn't really create these massive dusty galaxies until way later in time, which is this orange histogram you see here, whereas the observational data is this green, showing that their peak is usually around redshift 2 or 3. So it's a really big issue. We can't create them quick enough. We have issues creating enough dust and things like that. And related to their evolutionary path, our models also struggle to create massive quiescent galaxies. So we can't get them big enough and we can't kill them fast enough. And so you can see here, very briefly, the observations are in these like black points, and these are just as a function of redshift, and you were going increasing stellar mass. So the most massive quiescent galaxies are over here on the right. And you can see just with increasing stellar mass and with increasing redshift, our models are still struggling. We can't make them. There's a few more examples over here on the right. How am I doing for time? Okay, great. So I wanted to know if there was a way that we can take what we do know about dusty star-forming galaxies and try to kind of back out some of the information on number densities and estimates that we can't really quite grasp in the literature yet. We know a lot about these populations, but as I mentioned, each paper kind of says something a little bit different. There are this many, there are that many, and it can be orders of magnitude in discrepancy. So I wanted to know if it was possible to take all of that data, marginalize over it, and take in all that uncertainty and come up with an estimate for how many of these galaxies exist in the universe at a given period of time. I have a little bit of time to go through my model, so I'll very briefly justify it. So I mentioned gathering all the empirical data we could on dusty star-forming galaxies. This starts with the infrared luminosity function. That is the most complete way to capture infrared bright galaxies, is to just sum up all the infrared bright sources you see in the sky. But the problem is lots of things are bright in the infrared, especially also AGN, black holes, things like that. And I want to use this infrared luminosity as an indicator for star formation rate. So I need to correct that infrared luminosity for AGN contribution. So I do that. And then I work magic to derive the stellar masses using the star-forming main sequence. If you want to hear more about that, ask me afterwards. At the end, I get a nice distribution of dusty galaxies in a given period of time and their stellar masses. That's what you see here. This is a stellar mass function plot. So each little panel is a different redshift epoch from low redshift to higher redshift. And that most of the points in the colorful lines in the background kind of show that on this x-axis, they are unable to really create any massive galaxies beyond a certain number, usually 10 to the 3 times 10 to the 11 solar masses. My model does a pretty good job of doing that. It's the black curve. These points that do kind of agree, that's just a chance. 2 minutes, thank you. Okay, this is my favorite plot, so we're here. So I am fortunate, I integrate under that stellar mass function, and I say, okay, how many massive galaxies do I predict during a given epoch of dusty galaxies? And in the background, all these points here, these green ones, are actual direct measurements from the literature, and they just go to show you that it's oftentimes 1 to 2 orders of magnitude in discrepancy, and we are struggling. JWST will help a lot with this. So will next generation wide field sort of millimeter and sub-millimeter telescopes. But we are struggling. And so my model is this nice pink band in the background. I have something a little bit smaller in uncertainty, but still pretty wide. And then the UV-based estimates are here in gray. And so what I take away from this is dust-obscured galaxies, massive dust-obscured galaxies are just as important as UV-bright galaxies in the early universe. We just didn't have the information to prove that yet. But the best part of this plot is making this cognitive leap. There's a whole abundance of information that shows that that dusty star-forming galaxies are the ancestors to massive quiescent galaxies at high redshift, these rare, massive dead galaxies that we can't see. And so I implement a little bit of an evolutionary component in my model. And these we do have really great constraints on from direct observations, these massive quiescent galaxies, all these gray points. And my model does an excellent job at reproducing this population based on simple assumptions. So that is the strength of this model. We use simple assumptions to model the massive galaxy population. We don't need any wild physics to get to where we are. I'm very, very proud of that. The part that I'm most excited about is this order of magnitude build-up beyond redshift 3 of the massive galaxy population. And that is where I'll be spending a lot of my time as a Hubble Fellow. So I'll just focus on future work. The volume density of massive galaxies, both quiescent, dusty, and unobscured, should be constrained in the next year or two using upcoming surveys that I'm a part of. I'm very excited for. But really, really kind of moving into the space of understanding how a massive galaxy goes from gas-rich and gas-dominated to gas-regulated and then to gas-poor, all in the space of a few hundred million years, is my main focus. Is that good? Okay, great. Thank you.
Any questions from the audience, or any questions online as well?
Thank you. Great talk. Thanks. So you motivated studying these galaxies for understanding star formation and cluster formation at extreme conditions on the kiloparsec scales. Are you pursuing any project? I'm super interested, especially in like
on
star
kiloparsec
cluster formation. Yeah, like what would you use? Are we capable of actually resolving such scales on this?
Yeah. So most people right now have been using gravitationally lensed obscure galaxies, focusing on lensed GMCs, that sort of thing. And most of the time they're focusing on like editing limited, that type of like definition. Can you constrain any gas ionization properties? That's usually done with ALMA right now on lensed objects. But part of the reason, yes, it's easier with ALMA on lensed objects. You can do it on unlensed objects. I have a personal thing. There's a lot of uncertainty there, so it would be nice to have it without it. The part of the problem is, a lot of these galaxies are really compact, very nugget-like, so we don't get that much information, and when they're not, they tend to be patchy, and you have issues with over-resolving and ALMA and all that. Anyways, I do plan on pursuing multi-wavelength sub-kiloparsec studies, because also with JWST, we're able to finally compare the stellar component. So that is an intention. We should definitely talk more about that. Yeah. Anybody else?
One more minute.
We do have an online question.
Okay, perfect. Want to ask it, Sinclair? Whoever asked it can also unmute themselves.
Sorry, my name is Rohan. I wanted to quickly ask a question about, based on these models and your expectations, how low mass can we go in terms of like this dusty, obscured star-forming population? Because the idea I thought is that when you go to lower masses, maybe you're like also going to very low metallicities, and metals accompany dust. And so is there a sense for like how low this kind of population might exist?
No, there is not. I focus on massive in particular for this talk because of the lack of limitations. The lower in mass that you go, the more IR luminous, more typical Milky Way IR luminous you go. So you're talking like 10 to the 11 solar luminosities in the infrared. And that part of the spectrum is not constrained well out at higher redshifts just due to instrumental limitations. And so the way this model is set up and the way the dust obscured population is set up, at least in intermediate to high redshifts, we are not sensitive enough yet. We're getting there. Things like the Alpine survey is a really great place to look. I believe what is it called? Not the MOSFIRE galaxy, MOSDEF survey. They're focusing on like more normal IR luminous galaxies at redshift 2. So those sorts of kind of studies on more normal IR luminous and therefore more low mass galaxies are that's the cutting edge. It's happening as we speak. Please apply for more time to get more observations on them. I know I want them. Things like that. So no, we still don't know. So that's why I restrict this to the high mass end and the very IR luminous end.
Right. Sorry. I guess I was unclear, but to like rephrase it another way, say for like a 10 power 9 solar mass galaxy, would you do you think it's possible to basically produce similar levels of obscuration? Basically, can you get these levels of AV in those lower mass galaxies as well?
Yeah, that's a great question. I do think so, personally. I know in simulations in general, massive or not, we have trouble not blowing them apart before creating that much dust in solar mass. But I do think it's possible, even if you think about the kind of more starbursty situation we have with just some of our own satellites in the Milky Way, right? So I do think it's possible, especially in the earlier universe. But is it observed? I don't know yet.
Got it. No, thank you so much. That was great.
Yeah, thank you. Sorry, we had to cut you off. But thanks. Let's thank Ariane again, everyone in our session. And I think we have some announcements.
Okay, that is on. Okay. Before we break, just a couple quick things. So we heard back from Bob Gicking about the question about carbon offsets. So please check the Slack channel. Andy put his response in the Slack channel. So if you're wondering about that, and also Bob will be actually at Space Telescope tomorrow. So if you want to meet with him while he's here, like in person, his email address is also in the Slack channel. So check that out. I got a text from Pat Knezik, who is our program scientist at headquarters. And she talked to upper management in the astrophysics division about the struggle that we're having with getting out our responses to the review that we had last year, in context to what the leads have done and what the fellows have already done in response to those recommendations that the review had. And so there's a suggestion that Thomas Zurbuchen, I don't know how many of you follow him on Twitter, but he has a lot of followers. The suggestion was that he tweets out the things that the program has done, both the fellows and the leads have done in response to and sometimes even before the recommendations. And she wanted to know if you all as fellows were okay with that. Would you be comfortable with Thomas Zurbuchen tweeting out different things? Wait, what are you shaking your head? You said you were happy with this before.
It's really the fellow group diversity group.
Yes. So this is a test the waters, and then we'll put it in Slack and we'll ask them. Yes. So is anybody opposed to it? And actually, if you're opposed to it and you don't want to say so, come find me during the break, or find one of the leads during the break. Yes. What's the motivation? Thomas has a lot of followers on Twitter, and so the thing that Pat's worried about, she said, I told them we're struggling to get word out to the community about what actions we and the fellows have already taken in response to the review. And so, yeah, she said, could you ask the fellows if they're okay with having their efforts highlighted that way being
a few people seem to express concern that we weren't doing anything.
Yeah.
So we want people to know that we are.
I was just going to say, I'm confused about what are we trying to do and what are we trying to answer for you? Yes. Can you give us context?
Well, it's basically what Paul said. So Pat got the message yesterday that some of the that some of you were concerned that that word wasn't getting out about what we've done and what you've done in response to the recommendations. So I think. Yeah, and I think because someone asked, what are we doing? And we've had a few sessions at AAS. We had a webinar before the AAS. We've had community meetings, and they haven't been. Yes, I have no idea how to get this to you.
I'm new here, so I'm not very familiar with the topic. But if you want to announce something, why it's not put on the NFHB website rather than being tweeted on Twitter?
Nobody looks at the NFHB website.
I mean, all fellows who are applying, they're gonna be looking at, or applicants for fellowship are gonna be looking at the website, right?
You're right. The applicants who are applying for the fellowship this year will look, but the rest of the community may not. And we've had stuff on the website before, and a lot of people don't. They just don't really look at it. I didn't mean to take up the coffee break, though. The last final thing. So if you have concerns, come talk to us. Hang on a second. The last final thing is they've double booked the cafeteria right now, so there's a meeting with about 50 people in there. So still just walk in, get your coffee and your snack, whatever. They're immediately as you come in. I was just in there a few minutes ago. And then just either go outside or just sit on the far end where our food is during the break. But did you have anything else you wanted to add? No. Okay. All right. Sorry for taking up your coffee break.
So we reconvene at 4.
Yeah, at 4 for the panel, the
Career panel.
Career panel. Thank you.
I know, but everything they've done is public already. So there's no reason why you can't treat them.
Yeah. Yes, yeah, that's true. That's a really good point.
Yeah, we could summarize it.
We could do names, we could do
Okay, you've had, oh, there it is. I know you've had a couple of things. Okay, so yeah, you can do.
We have a number of questions, so yeah.
Okay, so it'll be there. Okay. Yeah, the Slido looks good. Right. You need the handheld mics.
Yeah, so
and then there's a little helmet.
I'll probably have this one.
Okay, it's muted right now.
Yep, great. Anwar is going to be over there on questions, and Anwar is going to be running with the mic.
Okay.
And then we'll take questions from a combination of both Slido and then also like in person.
Okay. I assume you'll have each of them introduce themselves.
Yes.
Say like a couple minutes.
Yeah, exactly. Yeah.
Okay, cool. Yeah, if you need another mic runner, we can help.
Mm-hmm. Yep. I think we should have everything under control. Yep.